Hello, everyone. Myself, Ankur Sharma. I'm coming from Saarland University, and I'm presenting a paper on HTAP processing. So, when okay, yeah. So when we talk about concurrent transaction processing, the first thing that comes into our mind is MVCC, right? Like most of the system nowadays, most of the main memory database system nowadays rely on MVCC. And when you look at the design of MVCC, how it works is whenever you have an update, instead of replacing the in-place value, you create a new one. You can order the versions like in whichever way you want, but like we are considering the newest version is always in place and the older versions go to the version chain, right? So when you update, it's not a problem, right? So it's fast, you just go and you update update in place stuff. But what happens when you have analytical queries which want to scan over this column? Then what happens is your versions might be stored on the version chain, and then that gets expensive because of random access that you have to do, and also the timestamp comparison to find the right version which you want to use, right? So how do we solve this problem? The best way to do it is to kind of have two systems, one which is quite optimized for scans and one which is quite optimized for the OLTP updates, right? And this has been done. Hyper introduced this using fork, where you have a system and you can fork the process out, and that fork can run analytical queries, right? And but this snapshotting can be expensive, right? Like if you talk about physically copying, that's out of the question when you have a lot of data. But even fork, like your database can constitute of a lot of other stuff that is irrelevant for the snapshot, right? So if you want to, I don't know, run an analytical query on one table or in a few columns, then you have to fork the whole process. And that can be really expensive. So let's first look at what are the options that we have to create these snapshots, right? The first one is physical snapshot, where you just memcopy this stuff, right? The second one is using fork, where you fork a process using the Linux system call. And the third one is rewiring that we introduced in VLDB 2016. So we'll go to all of them one by one and how they work. So physical snapshotting is very simple. So you allocate a new memory area, and then you just do a memcopy, right? So the throughput in this case is roughly 3 to 5 gigabytes per second, depending on the memory bandwidth that you have, right? And if you look at fork, how it works is each process has a page table, right? And instead of copying the data that you have, you try to copy the page tables. And how it works is it creates a new process that has a page table which kind of maps to the original pages. So instead of copying the data physically, you only copy the page table entries. And whenever you want to write, the operating system performs a copy and write. So with this approach, you get throughput of roughly 90 gigabytes per second, but it's highly dependent on how large is your process and how much data you actually want to snapshot. So there is no question when you don't have this choice of flexibility in this case. You cannot say that, oh, I just want to snapshot only a single column. That's not going to happen. So you have to snapshot everything. So in our VLDB paper, we introduce a term called rewiring, where you can file back your memory pages, and then you are able to reconstruct them. So the snapshot becomes cheaper, and you can use mmap to actually change the physical page that is behind the virtual page. So you use a file. This is like this physical pages can be a main memory file, okay? And then you have these offsets which actually point you to different physical pages which you can manipulate using mmap. Okay, so for creating a snapshot, what you do is you allocate a fresh memory area, and then you do a mmap call to the different offsets. So of course you have to do this manually, right? And when a write happens, then you have to handle it in the user space on your own. So when you want to write, you have to catch the write, maybe using a segfault handler that we used, and then you try to find which page was written, and then you try to find the offset that was backing this page. Then you manually perform a copy on write, right? And then you actually change the permission of that page so that the process can write. Okay, so you have to manually provide a segfault handler that does this for you. So for this case, we get a throughput of roughly 1 gigabytes to 1.2 terabytes per second. And this is a huge gap, right? And when you look at this gap, it's mostly because of the fragmentation that can happen. So each of these memory pages have a data structure in the Linux kernel that specifies the permission of this virtual memory area. And when you write to a specific random page, right, everything else may be read-only, but when you write a specific page, this data structure has to split, because this data structure only stores information about the set of pages which have similar permissions, right? So when you talk about a large virtual memory area and you write to a single page in the middle of this virtual memory area, it has to split in 3 different parts, right? And that can be super expensive. So when you look at the cost of snapshotting, you see that the more you write, the more fragmentation you create. And if you have a single VMA, which is the data structure that handles this permission inside the Linux kernel, you have way faster than fork, because you have only single mmap call. Locating this data structure is cheap because you don't have to traverse the whole tree, and the tree is small. But the more you write, the more fragments you create, and it gets harder to find this data structure. Okay, and the cost gets significantly higher, and you also like cross this border of fork at some point in time. Okay, and this can have a severe impact on the performance, right? Because usually you assume that sometime in the future you will always write every page, right? It's not that you only always write a single part, right? And if you can, of course, optimize this, but it would be really hard to completely implement this, like the whole memory management stuff for your system. So what we did is we looked at that paper and we found out the problems that we faced, right? And the limitation was the system call. And as long as you have smaller virtual memory area and maybe you're using huge pages, it's not a problem. But the moment you have a large allocation and you have and you're using small pages, this problem is terrible, because for each individual page, you have to have an mmap call to point it to the right physical page. And that can have terrible performance, because you're doing a system call for every page. You can, of course, group them into chunks, but then you're kind of using, I don't know, a huge page, right? And you also increase the granularity, right, of copying. When you perform a copy and write, you have to perform the copy and write on that granularity, right? And if you have very sparse writes, then this can cause problems. So what we did is we decided to explore Linux kernel and implement a trimmed down version of fork. So you can assume this as a memcopy implementation inside the kernel. So it's a kernel support of memcopy. And how it works is, so you can see that this has a very simple API. So you pass in a virtual address of the memory area that you want to copy and the length. And what you get back is a virtual copy of that virtual memory area. And it will be separated by the OS using Copyonwrite. So it's like a trimmed down version of fork, but inside the same process. So you don't go beyond the process. So you're not trying to create a new process. And how it works is, suppose you want to copy only 2 pages. Instead of copying the whole page table, I insert a few page table entries that will point to the same page. Okay? So it behaves like fork, but it is really flexible because you can actually copy at the page granularity. So any page, you can insert a page table entry that might point to the same physical page. Okay? So what it brings us is flexibility, like memcopy. And we support all types of pages, like file pack pages, anonymous pages, huge pages, small pages. And you don't have to care about the separation, right? Like, so the OS handles all the separation part using Copyonwrites. And the other big thing is that you have a throughput which is similar to fork, but is independent of the process size. So you can always say that I want to snapshot a single column for the query, or maybe a slice of the column, or maybe a slice of the table, depending upon how you store the data, right? So you can snapshot any part of the data at any time. So if you compare the performance, it's very linear, right? And if you look at this plot, here what we are trying to do is we have a 10 gigabyte process, and we want to only snapshot 200 megabyte chunk of data from the process. So like, as you can see, fork takes roughly 108 milliseconds, which is like forking the whole process. And VM snapshot is very consistent around 2-some milliseconds. And this is what we actually wanted to achieve, right? Like, you can snapshot flexibly at any point in time and fast. So what we did is we looked at MVCC and we tried to actually improve upon MVCC. Like we want to get rid of this overhead of scans from MVCC. So what you have is a single column, and you have when a transaction writes, they write at in the local memory. So they are not updating anything in the database itself, right? And when they commit, these changes are applied to the actual version. And what happens when you have an OLAP query? So when you want to run an OLAP query, you can snapshot that particular column which the query wants to run on. And what we do is we make the current version, or the version with the version chains, as the OLAP part. And the snapshot now becomes the OLTP part. So if you look at this OLAP query, the OLAP scan will run on the OLTP version that was there. And all the updates will go to the snapshot. And this Copyonwrite will separate them over time. Okay? So the OLAP query will run on the OLAP part, and the OLTP updates will be applied to the next one. And similarly, when the next OLAP query comes, you can snapshot again. Okay? And the good thing about this is when the snapshot is not being used by any of the queries, you can just garbage collect the snapshot. And this makes the garbage collection part of the version chains very cheap, because you don't have to go through them and mark them to be garbage collected later on, but whenever this snapshot becomes obsolete, you can just garbage collect it. Okay? So what we did with the experiments is we took the TPCC schema, and we took this 3 TPCC transaction as our OLTP workload, and we had a custom OLTP OLAP queries on TPCC schema that were single table, multi-table, only scans, and computation intensive. And what we measured is we measured against the fork version. So, so we designed a system which was capable of actually supporting everything, like snapshot isolation, full serializability, and read uncommitted, and also the fork version. And what we did is we measured the latency of each query, OLAP query, while running OLTP transactions at the back. So as you can see here is like for this, so SEE are this single isolation, normal MVCC, without any snapshotting. And they have really bad performance because they have to go through these version chains and do this, all these timestamp comparisons. And for this fork and our case, you can see that for fork, you have significantly higher snapshotting cost. And that totally depends on how long your query is going to run. So if you have a query that will run for a long, long time, it actually doesn't make any difference. But if you have a query that might not run for a long, long time, this snapshotting cost becomes significant. And what we do is we kind of achieve the performance similar to read uncommitted, as if you're just reading the in-place version. Okay? But at the same time, you have full serializability because this snapshot was created at a given point in time. Okay? And if you look at the sustained OLTP throughput, so in the beginning of like this time, like there was no OLAP queries, and the moment the OLAP query comes in, your throughput goes down. And over a period of time, you see that there is a high variance in the in our anchor. We call it anchor because you snapshot different number of columns and different size columns for each queries. But whereas for the other system, you see it pretty stable because fork cost is stable and other systems have a stable cost. So finally, to conclude, we provide VM snapshot, which is like a kernel version of memcopy. And I would say this, that it was really easy to implement. It's not a bigger deal. Like it's in the kernel. It has a lot of, and it also supports the latest version of kernel, even the 5-level page table that is available now. And it can even snapshot single column, horizontal slash, whatever you want to do. And we can get the performance for OLAP queries, which is similar to read uncommitted while having no overhead on the OLTP transaction. And of course, the implicit garbage collection, that when you kind of when you garbage collect the snapshot, all the version chains are garbage collected implicitly. Thank you.
Hi, there's something I don't get about the fact that you're saying if you don't do anything special, you're going to have to follow all these pointers. Yeah. What if instead, every time you had a new version, you pushed the old version to just a sequential append-only part of storage?
Yeah.
And then all of the old versions would be there.
Yeah.
And normally when I'm doing a scan, I don't really care about the order.
Yeah.
So it might be fine for me just to go through the primary table as much as possible and then just to go to that extra append-only storage for those things. Is that?
Yeah, but depending upon how many OLTP transactions you run on, this log can be really large, right? And if your query runs for, I don't know, a few seconds, then you might have to scan a lot of data, which might be irrelevant for the query itself, right?
I agree, but I agree. I mean, I agree, but I guess what I'm saying is it would do away with a lot of the random access part because there would all be sequential.
Of course, yeah. But like at the same, so you want to care about how much data is actually scanned as well. Like so you want to make this trade-off. So when you do something like a snapshotting, you are actually only reading the relevant information and not going through this log. And the longer your query runs, this log can be arbitrarily large to actually go through.
Yeah, I guess what I'm suggesting is it could be orthogonal to your current idea.
Yeah. Any other questions?
Okay, let's thank.
Thank you.